on this computer. So we have a rocket, and the first thing we want to find is its weight. So the weight is equal to mg. So this is 1,000 kilograms times g, and that's equal to 9,800 newtons. Okay. All right. Okay, that was the first one. And then the second question, is what is the total thrusting force needed to accelerate this rocket up at 16 meters per second squared? Okay, at 16 meters per second squared. All right, that 16 meters per second squared is from a net force. Okay, so the net force can be found by Ma. All right, and so the mass is 1,000 kilograms times the acceleration is 16 meters per second squared, and that's going to be 16,000 newtons. Okay, now that's the net force. That is the force that will accelerate the rocket. The total thrusting force of the rocket has to not only counteract the weight, but also accelerate it. Okay, so the total thrusting force from the engines is the sum of these two. Okay, it has to first hold it up, 9,800 newtons, and then it also has to accelerate it up. So the total thrusting force will be the sum of those, okay? Or 25,800 newtons. And that is the answer, 25,800 newtons. Okay? All right, questions about that? Questions about that? No? All right. I want to also go over the daily 2 for yesterday. Okay, now I have to pause this because I have to look at the question. So the first one was a conversion, 65 meters per second to kilometers per hour. So 65 meters per second. And my goal is to get kilometers per hour. Okay, so a conversion from meters to kilometers will be here. And then from seconds to minutes. And then from minutes to hours. Like that. So now I have my units all worked out. And then 1,000 meters in a kilometer, 60 seconds in a minute, 60 minutes in an hour. Okay, and so I get 65 times 60 times 60, and the whole thing divided by 1,000, which is going to turn out to be, 234. So the answer to this is 234 kilometers per hour. Okay, so that's a standard conversion that you might need to do. Okay. All right, and then the last question involved that trajectory of the ball, and it asked this time, what was the acceleration of the ball at position A? Okay, and the acceleration at A is the acceleration at every other point in the flight as well. It's always the same, negative 9.8 meters per second squared. Okay, this is the acceleration regardless of where it is in the flight. Immediately after release to immediately before it strikes the ground. The acceleration is always negative 9.8 meters per second squared. Okay, because it is acting, the only force on it, this from the other day, the only force on this ball throughout its flight, discounting air resistance, which we are, the only force on this ball is due to gravity. And gravity accelerates that ball vertically at negative 9.8 meters per second squared. Okay, as I was looking at those responses to each of these questions last night, I found that most people got it correct. Not all, so I'm not quite where I want to be, but we're getting there. Okay. Okay, are there any questions about either of these, the daily two from Wednesday? Okay, well, my goal today is to get through as much of the sample tests as I can. And that which I don't get through today, I probably will get through on Monday, because we have a half an hour on Monday as well. All right. Okay, so let's get some space here. So basically, it's not going to be, I'm just going to be rolling through and going through this sample test, okay? I am recording this, so if you want to view it later, you can. I'm going to start with the sample problems, okay? I'm going to start with the sample problems. Number one, probably go through a couple of markers. A car of mass 1,200 kilograms accelerates from rest at the rate of 2.5 meters per second. So, okay, so let my data take. So, for number one, we have a mass. I forgot what I said. 1,200 kilograms. That's the mass. It accelerates from rest. Okay? Accelerates from rest. 2.5 meters per second squared is the rate of acceleration. And there's a time of 6.5 seconds. All right. Part A, what is the final velocity of the car? Final velocity of the car. Okay, for my equation bank, I have V sub F is equal to V sub I plus AT. Okay, now, so plugging my values in, I get 0 plus 2.5 meters per second squared times 6.5 seconds. Just your standard motion equation problem. And that turns out to be, multiplying this out, 2.5 times 6.5, I get a little bit over 16, call it 16 meters per second. Okay, so there's a motion equation problem. Part B, if a force of 2,000 newtons is applied by the brakes, what is the car's acceleration as it slows down and comes to a stop? Okay, for part B, we're given the force and we're asked to find the acceleration. Okay. Okay. We can apply Newton's second law to this. F equals ma. Dividing out the mass will give us that the acceleration is equal to F over m, which is equal to 2,000 newtons over the mass of 1,200 kilograms. Okay, and that looks to be 1.6 repeating, right? Yeah, and I'm going to call it negative because the force is in the negative direction. I should probably have called that force negative. So the acceleration will be negative 1.6 repeating. I'll cut it off there. Negative 1.67 meters per second squared. Okay. All right. And then part C, how far does the car travel from the time the brakes are applied to the time the car comes to a stop? All right. So now we kind of have a new motion. We have a new motion equation problem. Okay. It started out with an initial velocity of 16 meters per second. And we actually keep the number because it's still on my calculator, so I'm just going to leave it there. Okay, and the final velocity is 0. The acceleration was negative 1.67 meters per second squared, and I want to find distance. Okay. You cannot use, incidentally, you cannot use VIT plus 1/2 AT squared is because I don't know the time that it took to come to a stop. That time is not 6.5 seconds. This is the time that it was accelerating from rest to this value. Okay, so we really can't use d equals VIT plus 1/2 AT squared. We're left with this option. Okay, so VF squared is equal to V sub I squared plus 2 times A times D. D is my unknown. So my V sub F is 0. My initial velocity, I'm going to keep the entire thing. If you cut it off at 16, that's okay. All right. Plus 2 times the acceleration, negative 1.67 times D. Okay, 16.25 squared. I get 264. So 0 is equal to, am I going to have enough room? Probably. 264 plus 2 times a negative 1.67, which is 3.3. So that's negative 3.3, repeating, meters per second squared times d. Subtract the negative 264 from each side. It becomes negative. I know that's going to happen. Times d. And then finally, divide everything by this.
Okay, literally the only thing that's going to be tough for me on this damn physics test is remembering the things, but I can literally just look at my notebook, so. The equations.
You realize, Parker, that I heard that.
Oh. This is so hard. I can't remember any of these, dude.
Well, that's what equation banks are for. Right? Right. So, okay, so everything cancels. Everything cancels except for a meter. Whoops, 1 meter. Notice it turns out positive. And that actually makes sense because the car is moving forward while it's coming to a stop. It's not going backwards. So it makes sense that the displacement turns out to be positive. And divided by 3 point, and I get 79.2. So the distance that it takes to stop is 79.2 meters. Yeah. Okay. And that's number 1. Questions? Yeah, the more organized you are with this stuff, the better. That's why I like to have all the equations in one place. All right. All right. Number 2. Student standing on the Golden Gate Bridge and wonders how high the bridge is above the water. He takes a rock and drops it from the bridge. He records that it takes 11.4 seconds. 11.4 seconds to hit the water. Okay? How high is the bridge above the water? All right, well, the initial velocity is 0. It's being dropped, so it's under the influence of G. And I want to know displacement. So this leads us to, I believe this was equation number 7. D is equal to VIT plus 1/2 GT squared. Right? So plugging this stuff in, V sub I is 0, so that term goes away. And I have 1/2 times negative 9.8 times 11.4 seconds. Don't forget to square it. Okay? And if you do that, 11.4 squared, you get 634. So 634 meters. 634 meters. All right. And that's number 2. All right. Questions, comments on that one? basic motion equation problems that you will see on the exam. Okay. Onward. Onward. Number 3, we have, it says, man walks with a velocity 1.5 meters per second at 300 degrees. Reference compass here, 0, 90, 180, 270. So 300 degrees is kind of going like that. So 300 degrees is sort of like that. Okay, and the velocity was 1.5 meters per second. So 1.5 meters per second. What they want us to find is the westward and northward components of the motion. Okay, so I'm going to draw in the components. There's the westward component. That's the northward component. And I have a triangle. That little angle there, 300 degrees minus 270 is 30. So I have a little vector triangle there, right? And then, what do I want? I want each component. So SOHCAHTOA. You know, I would actually advise you guys to make out a note sheet. You know, put everything on. If you were here, I would allow you to have a note sheet for the individual test. One sheet of paper, whatever you want to put on there, you can put on there. And so you might want to just have all the stuff so you're not just pages in your notebook. Because I'll say this, the test is going to take you most of the period. You're not going to have time to scroll through your notes and try to figure out how to do a problem. Okay, you have to come in prepared. If you have an idea that, oh, I'll just get the test and then I'll find the stuff in my notes, figure out how to do it, and then do it on the final exam. If that's your strategy, you're not going to finish. Okay, you're not going to finish in time. You have to be prepared for this. Okay, it is not an open-ended test. It's going to be due shortly after the end of the period. I always give you like 10 minutes beyond the end, but that's it. Okay. You're not going to have time to scroll through your notes, figure out how to do a problem, and then do it. You're going to have to know coming in. Okay? So just a word of warning there. The test is going to take you most of the period. All right? At least half of the period, even if you know your stuff up and down. Okay? Yes, the test is a Google form. That's the only way that I'm going to be able to do it. If I had only one class that sat for one period, maybe I'd do it somewhere else. But otherwise, I have to give equal time for everybody, right? And this is the way I'm going to do it. So yes, it is a Google form. You should show as much work as you can for the problems. Again, the more I see, the more partial credit I can give if the answer is wrong, okay? So you're going to have to work quickly, all right? Okay, so anyway, getting back to this. I have components that I can use SOHCAHTOA for. For the westward component, it's the adjacent side, so I'm going to use cosine. So cosine is adjacent over hypotenuse. Okay, multiplying both sides by 1.5. Then cancel. The westward component turns out to be 1.5 times the cosine of 30, which is 1.3. So this is 1.3 meters per second. The northward component is the opposite side, and that's related by the sine function. Sine of 30 is opposite over hypotenuse. Okay, so which is v sub n over 1.5. Multiplying both sides by 1.5 again. Multiplying both sides by 1.5. Cancel. And I get v sub n is equal to exactly half. Sine 30 is 0.5. So this turns out to be 0.75 meters per second. Okay. 10%. All right, sorry, 20%. The final is 20%. Looking in the chat window. 20%. Okay. It said, now, in case the finals are not supposed to change your overall average more than 10%. That's where that number comes from. But in my experience, 34 years doing this, it doesn't. It never changes it by more than 10%. Okay, unless you just complete a blank form, you know. But finals generally don't move you more than a half a grade, like from an A to an A minus or an A minus to a B plus. Only rarely do you jump from like an A to a B plus. You have to pretty much bomb it, or go from a B to an A minus. You have to kill it, you know, which is great if it happens. But in my experience, it doesn't move you all that much unless you just completely, you know, blow it off and don't prepare at all. Then it can. But generally, you pretty much land where you always do in the class. That's what I found. Okay, let's see. Working on number 4. 2 concurrent forces act on a 4-kilogram object. 40 newtons at 180, 60 newtons at 270. All right, talking about number 4. So 40 newtons at, what did I say? 40 newtons at 180. That's going down like that. And then 60 newtons at 270. It's going like that. And find the resultant force of the mass. Okay, so the resultant is going to be drawn. You can add them tail to tip as well, but the resultant will be drawn like this. Okay, one force pushes it to the left, and the other force pushes it down. It's going to go down and to the left, right? So magnitude can be found by Pythagoras. So 40 squared plus 60 squared is equal to the magnitude of r squared. Okay, and just rolling through the math, I'll save you a little. You should get 72 newtons for this. 72 newtons. Okay, now we need an angle. Now, it doesn't really matter which of these 2 angles you choose. Doesn't really matter. I guess I'll choose this one. Okay. If you choose, well, you're going to use tangent, right? And so this is going to be opposite over adjacent. This, of course, is 60 because it's a rectangle. So the tangent of x is equal to opposite over adjacent. Tangent of x is equal to opposite over adjacent. Opposite over adjacent. I can write that better. And now this matters. The angle that you choose matters for this one. The opposite is 60 over 40. If you chose that angle, it's the other one, 40 over 60. But I chose this one, so it's 60 over 40. 60 over 40. Which is 1.5. And then taking the inverse tangent of 1.5, that gives me an answer of, let's see here, 1.5 inverse tangent. I get 56 degrees. 56 degrees. Okay, that 56 degrees is right here, which I'm adding to 180. I'm starting at 180 and I'm increasing. So the bearing then is 180 plus 56. I started at 180 and I increased by 56, right? And 236. Doing math right. So then the resultant, my answer then, resulted 72 newtons at 236 degrees. Okay, questions? Okay. Next part Next part, it says determine the resulting acceleration of the mass. Well, if it's under a 72 Newton force and it gave me a mass of 4 kilograms, right? I think it was 4 kilograms. Yeah, mass is 4 kilograms. So I can find the acceleration by Newton's second law. So the acceleration is the force divided by the mass. And so if it's 72 newtons and the mass is 4 kilograms, then the acceleration will be 72 divided by 4, which is what, 18? I'm doing my math correctly? 18 meters per second squared. And I should probably also indicate the direction. This is going to be in the same direction as the force, 236 degrees. The acceleration is always in the same direction as the force, as the net force. That's part of Newton's second law. Okay? Okay, and then finally, let's see, how am I doing for time? Pretty well. Determine the equilibrant. The equilibrant is the force that puts this system into equilibrium. And that force would point opposite to the resultant. We talk about that. The equilibrant force is the force that puts this system into equilibrium. And I will say that, I'll say that on the test. The force that puts it into equilibrium. It's going to negate this resultant. It's going to have the same number of newtons, but in the opposite direction. Okay, so for part C, I guess I can put that right here. Part C, it's going to be the same number of newtons, 72. And it's going to be in the opposite direction. So I'm going to take this direction and I'm going to subtract 180. I'm going to take the resultant, the direction of R, I'm going to subtract 180. And so 236 minus 180. 236 minus 180, that gets me back to 56, actually. So my answer for this, the force that puts it into equilibrium is 72 newtons at 56 degrees. Okay. Expect one of those. Are there any other questions? Are there any questions? You can expect one of these on the exam, okay? Any questions I can answer? Okay. All right. Next. A box of mass 5 kilograms is being dragged by a rope. So a box of 5 kilograms being dragged by a rope. And the rope is at an angle of 25 degrees to the ground. 25 degrees. And the tension in the rope is 40 newtons. Okay. There's my information. Part A, determine the horizontal and vertical components of the force. All right, so here's my horizontal, force horizontal, whoops. And there's my force vertical. Okay, now, let's see. Force horizontal is the adjacent side, so I'm going to use cosine. So the cosine of 25 is the adjacent, F sub h, over the hypotenuse of 40. And multiply both sides by 40. Cancel, cancel. And this is going to be 40 times the cosine of 25, which, according to my answer sheet, 36 newtons. I hope that's right. Better check that though. Times 40. Yeah, 36 newtons. So that's 36 newtons. And then for force vertical, I'm going to use the sine function because it's the opposite side. So sine of 25 is force vertical over 40. Multiply both sides by 40. Multiply both sides by 40. And cancel, cancel. Force vertical is equal to 40 times the sine of 25, which my calculator says 16.9. I called it 17. Okay. 17 newtons. Okay. Stop me at any time for a question. Okay. Part B. What normal force does the floor exert on the box? Now, the normal force is the force that the box, I need some space here. I should have looked ahead. Let me do this. 36 newtons, 17 newtons. Now, the normal force is the force that the floor exerts on the box. Now, under normal conditions, it would simply match the weight. Okay. Excuse me for just a minute. Yeah. Okay. Sorry. I have a computer in the back of the room, one of my room computers. I'm using as a monitor, and it went to sleep on me. So, okay. If the force weren't there, if this rope force weren't there, the normal force simply matches the weight. Okay. And I can find the weight by mg. If I have 5 kilograms times 9.8, okay, 5 times 9.8 is 49 newtons. Okay, 49 newtons. So that's this, the value of the weight. If the box were just sitting on the table, okay, that normal force would match it, and it would be 49 newtons. But in this case, the rope takes some of that weight off, and so the forces up equal forces down for equilibrium, right? The force down is 49. Let's write it like this. Forces up equal forces down. The forces up are the normal force plus 17. The forces down are the 49 newtons of weight. So you get this. Okay. And then by subtracting off the 17, we get the, let me write that up. By subtracting off the 17, we get the normal force, the force that the table pushes back on the book, or the box rather, is 32 newtons. There's your answer to that. I didn't really do that very much, and so frankly, I won't put a question like this in the final exam, but that's, if I had a little more time when I was doing that unit, I would have done stuff like this, but honestly, I didn't. So you can basically ignore that part, that one. And then part C, what tension in the rope would be necessary to accelerate the box at 3 meters per second squared? Okay, so I want an acceleration of 3 meters per second squared. Okay, this is going to require a force, a net force. Okay, and the net force, well, there's actually no friction here. There's no friction, so this is just going to require a force of ma. And that ma will be 5 kilograms times 3 meters per second squared. Which is 15 newtons. Okay, so this actually this actually changes this force horizontal. All right. So let me get some space here. Okay. So now the net force. Oh, wait a second. No. Oh, you know what I meant to say? What I did not say in this problem, and that I should have included, was it was being dragged at constant velocity. Shoot. Would you please add something to this? Add something to this question. For the text, say a box of 5 kilograms is being dragged at constant velocity. Put these words in there. At constant velocity. I meant to include those words. So what it should say is a box is being dragged at constant velocity. Okay. By a rope, dot, dot, dot. A box of mass 5 kilograms. Sorry, I meant to include the words at constant velocity. I want to put that in there. Okay, so add those words. Okay. Now, actually, before I address this, I'm going to come back to this. But I could have asked an additional question, and I probably should have. Okay. But I can ask it now. What is the force of friction? Okay. What is the force of friction? This box is being dragged at constant velocity. What is the force of friction? And what you have to what I'm kind of getting at here is when it's at constant velocity, the forces match. If or at constant velocity, the friction force is going to be the same as force horizontal. If it's being dragged at constant velocity, there's no net force in the horizontal. So that means that this component, 36 newtons, is exactly matching friction. Okay? All right? So I know then the force of friction is equal to 36 newtons. Okay? And then getting back to my part C, if I wanted to accelerate at 3 meters per second squared, that's going to require a net force. Okay? I need an additional force to actually accelerate the box. And that accelerating force can be found from MA, which is 5 kilograms times 3 meters per second squared, which is 15 newtons. And so then, okay, then I would need more than 36 newtons. Okay? How much more than 36 newtons? To accelerate it, force horizontal equals 36 newtons plus the net force, F net. So then force horizontal has to be 51 newtons. Okay? All right? I'm going to need more than 36 newtons. 36 newtons was required to drag it at a constant velocity. I need more than that to accelerate it. So I'm going to need 36 newtons of horizontal force to overcome the 36 newtons of friction. Okay, I'm going to need more than that. How much more? 15. So I need a total horizontal force of 51 newtons. Okay? You know, looking back, I should have written that question better. For one thing, I should have included those words at constant velocity. And I also should have had another part in there to ask you, what is the friction force? Okay. And the answer to that question is right here. At constant velocity, the friction force and force horizontal are equal. Okay. So sorry about that. I didn't write that question very well. Now we're actually still not done with this. Okay. We're still not done with this because the question said, what is the tension in the rope? So now I have to draw a new vector triangle. I have to draw a new vector triangle. There's the tension in the rope. I want 51 newtons of horizontal force and a 25-degree angle. Okay, so I'm really asking for, what is the tension in this rope? Okay, adjacent, hypotenuse, cosine function. Cosine is equal to adjacent, 51, over hypotenuse, t. All right. Multiply both sides by t. Actually, what's cosine of 25? I get 0.906. So t times 0.906 is equal to 51, and then t is equal to 51 over 0.906, which turns out to be 56 newtons. Okay, 56 newtons. So apologies for the poorly worded question. I'll proofread my final and make sure I didn't do something like that on there too. Although I've already proofed it once, but I'll proofread it again just to make sure. Okay, that was kind of a tougher problem. You know, kind of brought a bunch of things in. We found the components, talked about the normal force, but you don't really have to worry about the normal force. But then instead of the normal force, I should have talked about force of friction. At constant velocity, okay, keywords, if you see the words at constant velocity in one of the items, that generally means something important. Like this, force of friction, horizontal force have to match, okay? They're not there just to take up space. Okay, they're there to give you a key piece of information. Okay. Okay. Questions, comments? All right. Okay. So those are the types of problems that I can ask you on the exam. How to study for this? Do the homework problems over again. Where am I going to put the recording? I'm going to put it right in this week's folder. You know, after it renders, it's going to take a little while to render, and then I got to save it to YouTube, and then it's going to. I'll put a link to it in this week's folder. I'll say link to December 10, 11 presentation. Okay, it'll be in this week's folder. All right. Okay. True, false, number one, 100 centimeters a meter. True. Number two, 4.6 times 10 to the 7th. No, it's 4.6 times 10 to the 5th. So that's false. Number three. Oh boy, that's a conversion. Let's see. 75 miles per hour. 75 miles per hour. What do we want to get to? Feet per second. All right, so I need feet in a mile. I'll get that. And then hours to minutes. And then minutes to seconds. And I get feet per second. Okay. 5,280 feet in a mile, 60 minutes in an hour, 60 seconds in a minute. So let's see. I get 75 times 5,280 divided by 60, and I get 110. So 110. 110 feet per second. What did it say? Oh, 110 feet per second. So that is true. That is true. Okay. Let's see. General equation for a linear relationship is y is equal to kx, where k is the slope of the line. That is true. Number 5, displacement is a scalar quantity, whereas distance is a vector quantity. False. It's the other way around. Displacement is a vector. Distance is a scalar. 6, velocity is defined as speed in a particular direction. Yes, it is. Yes, it is. 7, acceleration is a vector quantity. Yes, it can be positive or negative. 8, an object dropped from rest for 4 seconds will acquire a speed of 39.2 meters per second. Drop from rest, 4 seconds. G is negative 9.8. What is the final velocity? V sub f is equal to vi plus gt. V sub I is 0. I get 9.8 times 4. I'm working quickly because I'm under a timed conditions here. I'm not going to worry about units, but 9.8 times 4 is 39.2, and that's true. That's true. Number 8 is true. Using a motion equation. Number 9, an object projected upwards with a velocity of 49 meters per second will hit the ground 5 seconds later. All right, so projected upwards, 49 meters per second, and we'll hit the ground. So I'm looking for the time of flight. Well, we use that little trick of final velocity to 0 and half the flight. This is an initial velocity. So I'm going to use VF is equal to VI plus GT. This time VF is equal to 0. VI is equal to 49 plus negative 9.8 times T. Bring the 49 over. Divide out the negative 9.8. And I get T is equal to 49 divided by 9.8, which is 5. But that 5 seconds was to the top. It asked us, or it said, it will hit the ground 5 seconds later. Now, it takes 5 seconds to get there, takes another 5 seconds to get down. So it's actually 10 seconds to get to here, 5 seconds to get to here. So it's false. False. Okay, number 11. Slope on a distance time curve indicates velocity. Yes, it does. Yes, it does. Okay. So distance time. All right. Change in time or change in distance over change in time. And that is velocity. Yes. That is velocity. Slope indicates velocity for a D versus T. 12. Acceleration on a distance time graph is indicated by a straight line of non-zero slope. Like this? No. This is CPV. Acceleration would be a curve, either concave upward for positive acceleration, concave downward for negative acceleration. So on a D versus T, did say D versus T, right? Yes, distance time graph. No, that's false. It's not a straight line. 13, area under the curve, velocity time graph indicates the acceleration. No, it doesn't. It indicates the displacement. Okay, for a V versus T. For a V versus T, the slope, delta V over delta T, okay? Rise over run, if this is meters per second, and this is seconds, rise over run gives you acceleration. Instead, area is one dimension times the other dimension, length times width And that gets you meters for displacement. So the area gives you displacement. The slope gives you acceleration. Okay? For a V versus T. All right. Let's see here. Where are we? 14. Object in motion tends to stay in motion unless a statement of Newton's third law. No, that's Newton's first law. That's Newton's first law. Third law is action-reaction. Number 15. Acceleration produced by an unbalanced force is always in the same direction as the force. That's true. That's part of Newton's second law. Number 16. At terminal velocity, the net force on an object is 0. Terminal velocity, remember? Remember what terminal velocity was? It's where the object was falling through air, and the air resistance matched the weight. So it fell with a constant speed. It accelerated at first until the air resistance pushed against the object, and now they match, so it falls at a constant speed. And if it falls at a constant speed, the acceleration is 0, and therefore the net force is 0. So let's see, is that true or false then? The net force on the object is 0. Yes, true. All right, number 17. Three forces act along the same line. On an object, they have magnitudes blah. The net force can never be 0, regardless of the directions that the forces point. So I have three forces. 25, 20, and 15. They can either point in the same direction or anti. Can they ever add to 0? And the answer is no. You know, what's the minimum that they could produce? Well, the minimum they could probably produce is if I have the 20 and 15 going that way, 25 going that way, that's going to give me 20 to 35. The minimum this thing could produce is 15. Check it, 10, 20 plus 15 acting together, opposing the 25. That's the minimum that these could produce, acting either in the same direction, you know, together, or opposite. So the answer to that is, let's see, can never be 0. True. Okay, 18. How am I doing for time? All right. Rocket problem. Weighs 1,000 newtons. So a rocket here, not a very good rocket. Weighs 1,000 newtons. The engines put out a total force of 5,000 newtons. So the force applied is 5,000 newtons. The rocket accelerates upward at 5 meters per second squared. Okay, I agree that the rocket accelerates up because the applied force is greater than the weight. So yes, if it just said the rocket accelerates upward, that would be true. But if it set a rate at 5 meters per second squared, now we have more work to do. So I do have a net force up. Okay, and the net force, 5,000 up, 1,000 down, gives me a net force of 4,000 newtons. I gotta write this out better. Tell you what, I'm just gonna write F net over here. And we'll do the work over here. So the net force is going to be the 5,000 newtons up plus a negative 1,000 newtons down. So the net force that accelerates that rocket is 4,000 newtons. I have to counteract the weight, right? Okay, now if I wanted to use this force to find the acceleration, F equals ma. So acceleration is equal to force divided by mass. Force is 4,000 newtons. What am I going to use for the mass? I'm not going to use 1,000 newtons. That's its weight. That's not its mass. So if I wanted to find the mass of the rocket, I'd have to do more work still. 1,000 newtons is equal to mass times negative 9.8, or just 9.8. That's going to be on the order of 100 something. kilograms, right? So I'd have to do more of that, but I don't have to for the purposes of this question. I already know that it's false. I already know that it's false. It's not going to accelerate upwards at 5 meters per second squared. It's going to be less than that. Okay, because of the force. You know, the way somebody would get that would just take 5,000 divided by 1,000. That's incorrect for a number of different reasons, actually. Sounds definitely false. All right, number 19. 19. Two force vectors have magnitudes 20 newtons and 30 newtons and can point in any direction. All right. If they act concurrently on an object, and what that means is they act on the same object. Okay. It says nothing about the direction. It just says they're acting in the same direction, right? Or they're acting on the same object. Okay, now 20 newtons and 30 newtons. If they push in the same direction, they have a maximum of 50. They would have a minimum of 10. Okay. And then if I had them pointing in, other directions, they could have some value between that. So the range of these forces would be 10 to 50 newtons. Okay, they can't get 8. The statement is false. They can get anywhere from 10 to 50, inclusive, but they can't get 8. So that statement is false. Okay. 20. I got a river problem. Boat on a river problem. So here's my river. Here's my boat. Okay, what does it say? It says can travel at 24 kilometers per hour. It is aimed straight across the river. Oh boy. At 24. The current is flowing at 10 kilometers per hour. The resultant speed is 26. Oh, it gave me 2 kilometers wide. The resultant speed is 26 kilometers. The resultant goes like this. And I can find the magnitude by Pythagorean theorem. So 10 squared plus 24 squared is equals the resultant squared. And as it turns out, it is indeed 26. So that statement is true. Okay. Now, what did the 2 kilometers wide have to do with it? It didn't. Okay, it's just extraneous information. So the statement is true, 26 meters per second, or 26 kilometers per hour. All right. 10 minutes to do 2 problems. 2 forces act concurrently in an object. One. All right. What do I got? 5 newtons at 90, 8 newtons at 180. So 5 newtons at 90, 8 newtons at 180. And what, the equilibrant vector. Okay, well, first of all, I have to find the resultant. The resultant is going to be, where's red? This, that's R. I got to find the magnitude by Pythagorean theorem. 5 squared plus 8 squared. 25 plus 64 is 89. Square root of 89 is between 9 and 10. 9.4. So the resultant is 9.4 newtons. That's my magnitude. I need an angle. X, take that angle there. So that the tangent is equal to opposite over adjacent. 8 over 5. 8 divided by 5 is 1.6. X is equal to the inverse tangent of 1.6, which my calculator says is 58. So this is 58 degrees. That's 58 degrees. All right. I tack that onto 90. So bearing is 90 plus 58, 148. And so my resultant vector was 9.4 newtons at 148 degrees. Okay, now it wanted the equilibrant. That's the one that, oh, I didn't give myself enough space. That's the one that goes opposite to the resultant. Same number of newtons, 9.4, and I have to add 180. 148 plus 180 is 328. So 9.4 at 328. Oh, yeah, that's what they gave us. So that's true. The statement is true. Okay. And then, let's see here. Number 22, the last one. Last one. Box being dragged along the floor. Tension is 200 newtons. Angle is 30 degrees. And they want the horizontal component. There's the horizontal component. There's the vertical component. Horizontal is cosine, so the cosine of 30 is equal to f sub h over 200. Multiply both sides by 200. Multiply both sides by 200. And I get and when I do that on my calculator, it does not say 100. Okay. Instead, it says 173. So that statement is false. So it's actually, if you worked it out, the vertical component has a magnitude of 100 newtons, but not the horizontal component. Okay. And that's the true false. All right. Okay. All right, I'm going to save the multiple choice for Monday. We have a half an hour on Monday. Now, our test, I'm going to have to pause this. The final exam consists of 15 true false that are worth, I think I had them worth 3 points apiece. 15 multiple choice that are worth 4 points apiece. That's going to be a total of 105. And then I'm going to have 95 points worth of problems to take you to 200. The actual amount of points really doesn't make a whole lot of difference because it's not tacked into a semester grade or anything. It stands alone as a test. So it doesn't matter if there's 100 points or 200 points or 1,000 points. It doesn't really matter. But the more points I make a problem, the more partial credit points I can award. I don't have to think, well, is this worth 4 or is this worth 3? You know, if it's worth, if the problem is worth 5 points, something that I had to make a differentiation. If it's worth 10 points, I could define it a little bit easier. So that doesn't mean a whole lot to you, I guess. Otherwise, it's going to be out of 200 points, but it'll show up as a percentage in your grade book. Okay. That's all I think I'm going to do for today. Do you have any questions for me? final exams are kind of high stress. It is a Google form, all right? And I thought that would be the easiest. And once again, there will be about eight problems, something like that, that kind of mirror the ones that I went through today. You'll have a couple motion problems to do. You'll have a component problem to do. You'll have a resultant problem to do. And dragging a box across the floor with friction involved, you'll have one of those. And so it's not, you're not going to be surprised. It's nothing that you haven't seen before. The final exams are not difficult in terms of the difficulty of the problem. They're difficult in that you have to remember how to do so many different things. That's the stress of finals.
I have a quick question, Mr. T.
Fire away.
So since it's a Google form format, would you still like expect us to be putting our work onto the form?
What I said is put as much work as you can. So again, the more work I see, the more partial credit I can award. So I don't want you to necessarily type out a book, but if you're getting individual, if you need to calculate the final velocity to calculate something else, put down your answer for the final velocity. Yeah. And try to, if you can, very quickly type in the equations that you used. If it's a 10-point problem, and that's going to be typical, I have 95 points to divvy up in about 8 problems. So there's going to be some 10-point problems. And if all I see is the answer, and it's an incorrect answer, I have to take off 8 or 9 points, which I really don't want to do. But the more work I see, oh, they used the right equation. Oh, the copy step is right. They must have just entered it into their calculator incorrectly. That's only a point, maybe 2, So the more work that I see, the more partial credit I can award. That's the theory behind that. All right. Now, it takes time to type stuff in. It also takes time to write stuff down. So rather than just write everything down and then retype it, try to do as much work in the form as you can, okay, to save you time. All right. But yeah, the more work I see, the more partial credit. If the answer is right, then the answer is right, But if it's wrong, then I want to see where it's wrong, because sometimes mistakes are minor, sometimes mistakes are major, and the number of points that I award are different in each case. So I always say more is better. Okay. All right. Are there any other questions? Oh my gosh, I went over time. Okay.
For the bonus or the extra credit that we could get,
Yeah.
is that the whole sheet, or is it just the bonus opportunity ABCD?
The first 2 pages of it were just a tutorial about how to do it. The bonus point
Okay.
problem actually is on page 3. Find the resultant of those four vectors. Okay.
Hey,
Yeah.
thank you.
The first 2 pages are just tutorial. So if you only want to scan in that last page with all the work on it, that's great. I don't need the entire form back, just your work. You can put it on a separate sheet of paper as well. It doesn't matter. Okay.
Thank you.
You bet. And that's where 10 test points. All right. Sorry to go over time. I kind of got long-winded there. Any other questions for me? If you have any other questions for me? All right. Well, I wish you all the best of luck. I will, and have a great weekend, and I will see you on Monday.